last program that you might have seen in this tutorial series was slightly different. In this series, what I've tried to do is to take some of the basic principles of physics that you learn about at school and show how useful they are here in Bhutan. The last program that I made was about nuclear fusion. Now that's a bit out of the normal pattern, because I have to tell you, nuclear fusion is not on your school syllabus. Perhaps that's a fault of the syllabus. I believe nuclear fusion will be so important in the future it should be, but it's not. There is no nuclear fusion in Bhutan at the moment, but the implications of the future of nuclear fusion for Bhutan are very, very considerable. So hence I offered you that little program to explain what nuclear fusion is. Well, now we come back onto our mainstream programs now, and this program is going to be about light waves. Light waves, what are they? Light waves, what do they do? And in particular, about a very useful little device called a laser. Now, a laser, spelled L-A-S-E-R, it's actually an acronym. Laser stands for Light Amplification by Stimulated Emission of Radiation. I'll mention that again later. So remember, laser is an acronym with a meaning. And we'll have a little look at a very basic idea of how a laser works, and then look at some of the phenomena of light that you learn about in school. So, light waves. Magnetic waves, a mixture of an electrical force and a magnetic force. It's actually a bit strange. If you could imagine me taking a magnet and a comb. I actually haven't got a comb here, but can you imagine this board writer is a comb? A magnet and a comb. The magnet gives out a magnetic force around it, and if I rub the comb on the sleeve of my Go, then you probably know I can pick up little bits of paper with it. I get an electric force around the comb. So a magnet and a comb. Magnetic force, electric force. Look at that little point in space just there. Now it's feeling an electric force. Now it's feeling a magnetic force. Electric force, magnetic force. If I were to do this several thousand millions of times, I'll repeat that, several thousands of millions of times a second, I would produce just here a light wave. What a light wave is an electric force, a magnetic force, electric force, like that, changing millions of times a second. Now, we know electromagnetic waves form a spectrum, and we've looked at the little bit of the spectrum which is the visible spectrum, which goes from red right the way through to blue. Long wavelength, short wavelength. Long wavelength, short wavelength. High frequency, low frequency. Note, I have to say long and short wavelength and low and high frequency. Between red and blue, we have the visible spectrum. We get the various colors: red, orange, yellow, green, blue, violet. And somebody asked me the other day, does color really exist? Well, color doesn't really exist. Color is just in our heads. If you get a particular frequency of electromagnetic wave, that comes into the eye. The eye and the brain are sensitive to that frequency, and our brain will tell us that is what we call blue. A different, lower frequency of electromagnetic wave, and our brain will tell us that's what we call red. The color is only generated in our brain. Colour doesn't exist if there were no people. Colour is something created by ourselves. Colour does not exist without us around to interpret the colour. So the electromagnetic spectrum, a tiny little bit of it, is the visible spectrum. And so when we talk about light waves, we're talking about just those frequencies or wavelengths of electromagnetic radiation that we can actually detect with our eye. Just imagine things like radio waves are electromagnetic waves. I wonder what we would see if our eyes were sensitive to radio waves and to X-rays. The world would be very, very different. Some insects have eyes which are sensitive to colours that we, the human being, cannot see. It's very similar with sound waves. A dog can hear a much higher frequency of sound than a human being can. So the dog can hear things we cannot hear. What would it be like with electromagnetic waves if we could see frequencies that at the moment our eye is not sensitive to? It would be a very, very bright world with all the radio waves going around us all the time. So that's something to think about. What we see is only because of what our eyes are sensitive to. Let's look a little bit more at lasers, light waves, and some of the things you learn in school. Some of the phenomena, some of the effects that we see with light. And this is a laser. And if I press the switch, you can see the very, very bright green spot of light, which comes from my laser. Now, I should warn you, a laser can be very dangerous. This little spot of light contains a lot of energy, and you must always be very, very careful never to let the light from a laser shine into your eye. This laser is sufficiently powerful. If this shone into your eye for more than a second, you would go blind. So please be careful with these things. However, the laser is a remarkable thing. It was invented, or shall we say thought about, way back in 1960, some 50 years ago. And I actually went to a lecture given by the man who invented the laser. And the problem was, it was just thought to be a little bit of a theoretical idea with no practical applications. The laser that he made was about the size of this studio. It occupied a complete room, and nobody could think of any uses for a laser. However, as we shall see, today we depend on lasers for communications. It's how your DVD player works. We can use a laser for surveying. We can use a laser for carrying out operations, because this high-powered beam can actually cut through tissues. We can use a laser for welding. We can use a laser for so many, many important applications. The most obvious one that you would come across is in your CD player or your DVD player. So can I just quickly say a word about how a laser works? Here's my laser. We've got a battery, and the battery occupies that much of this laser. The actual laser itself is just this section here. And then we've got a little lens in the front. So the battery, the laser, and a little lens. What's in this bit, the laser? Well, it's actually very complicated, but I'll try to make it simple. we've got a material in there with a complicated chemical name, which I'll show you in a moment. And it's like a little tube. One end has got a mirror on it, and the other end has got a mirror which lets some light through. So a little tube of material, a mirror at each end. And then we've got a little source of light, a little LED, like you find in an LED torch. And when that LED light flashes, it excites all the atoms in this material here, in this little tube. Now, when I say excite, it means it makes them energetic. They have a raised energy level. And then suddenly, on a trigger, electrical trigger, they all release their energy at the same time. And the energy comes out as light energy. It all comes from every atom at the same time in a synchronized way. And I've asked some people in BBS to help me show you that with some balloons, where think of the balloon as an atom. The blown up balloon has got energy, and then they can let it go. So I've explained that a laser works because all the atoms in the material in the laser become excited in a very energetic state. And then they release their energy. Well, how is that different from a normal light bulb? Well, what happens in a normal light bulb is that the atoms give off their energy all at random, one atom, then the other, then another, and in all different directions. And I've actually gathered together all the cameramen in BBS, usually they're on the other side of the camera, this time they're being filmed, to see if they can show you, first of all, how an ordinary light gives out light. Not a laser, an ordinary light. And they've got yellow balloons in their hand, which are atoms. And I'm going to tell them to excite their atoms. Right, let's see your excited atoms. Hold them up. In an ordinary light, the atoms give off their light energy in all sorts of different directions at random, not all together. Let's see the cameramen do that. Go. And that's how the light energy comes off with an ordinary light bulb or fluorescent tube. Now let's see what a laser does. Right, let's see the excited atoms. And now the difference is this. In a laser, all the atoms give off their light energy at the same moment in the same direction. Are you ready, cameramen?
Yeah.
Yes.
Go! Well done. So this makes the light that comes from a laser beam much more powerful, and it all comes out in one direction. That's why a laser beam is very narrow and travels miles and miles and miles. A laser stands for, you'll remember, light amplification by stimulated emission of radiation. The light is amplified because they let off their balloons when stimulated by me saying go, and they emitted the energy from their atoms or balloons all at the same moment. Light amplification by stimulated emission of radiation. So when you want to think how a laser works, remember all the BBS cameramen there letting off their balloons. Thank you. So the reason a laser light, or the light that comes out from a laser, is different from the light that comes out from an ordinary torch is because of this point, that all the atoms get rid of their energy at the same moment in the same direction. And that gives us a very powerful, very narrow beam of light, at a very exact, very precise frequency. And it's these properties of laser light which make it so useful. We can focus laser light down to a tiny, tiny point of light. And we use this to make a DVD player work. So, the laser. We've looked at a very, very simple idea of how the laser works, but what's really important is how useful the laser is. I'm going to use this laser to help show you some of the basic phenomena of light, the things you learn about in school, reflection and refraction. But before I do that, let me tell you about two very, very useful ways in which the laser can help us. First of all, you may be aware that in Bhutan the old way of measuring land was using a chain, an iron chain. And one of the problems about using an iron chain is that it's jolly difficult to get an absolutely perfect straight line with it. And this gave rise to lots of land problems where land was wrongly measured, land was incorrectly measured, and we have problems like excess land and all this sort of thing in Bhutan. Well, now all that issue has been solved because in the survey department they use a very sophisticated laser measuring instrument, and one of the advantages of the laser is it gives you a perfectly straight line. Let's go and visit the Land Commission and have a look at how they measure land. And so we've come here to the offices of the National Land Commission, and here's Mr. Gurung, who has been involved with surveying in Bhutan for many, many years. Mr. Gurung.
Yes, we were using this type of chain for the measurement, which is not accurate.
So one of the problems with the chain, Mr. Gurung, is that with a chain, especially over rough ground, it was very difficult to get a straight line.
Yes, it is. Our country is very, very undulating, so that by the chain we can't measure straight measurement.
So now, with the laser, you can actually get a very straight line.
Yes, now we are getting the very straight, very accurate straight line measurement by the laser beam. This is a modern technique instrument which is having facility of laser, by which we can make a measurement, very straight measurement. So instead of using chain, we are using this instrument.
This is the standard international warning label for a laser. It warns us that there's a laser inside this machine. And why do we need to be warned? We need to be warned because sometimes a laser beam coming out, going into your eye, can be quite dangerous. So this is the warning label to show there is a laser inside this machine. So we've said a word or two about how a laser works. Very, very simplified idea of how a laser works. And we've seen how a laser is useful in surveying land. In Bhutan, the old way of surveying land with a chain gave rise to lots of land disputes and excess land, and a laser now makes surveying very, very accurate. A laser is also really useful for something much more fun, and that is making CDs and DVDs work. So let's just quickly look at a typical DVD player that's on sale in Bhutan. We've come to Norzim Lam, to Carcel's store, to look at a DVD player, not because we want to buy it, but because a laser is what makes a DVD player work. And it's a laser which allows one to turn this shiny disc into a film, into music, or into all the other things we watch on a DVD player. If we turn the DVD player round, we can see that written on the back of the DVD player it says Class 1 laser product. So there's a laser in a DVD, and I'm going on to explain how a DVD player works and how a DVD or CD disc works. How does this work? Why does this depend on a laser to make it work? Well, a very quick explanation. Let me begin by inviting you to think about a black line, and here on the board I've drawn a black line. Now, here I've drawn an enlarged view of this black line, and you'll see that in some places I've wiped the black away, and so it's black, white, black, white, black, white. Now, if I shine a light on this, where it's black, I'll get no reflection of the light. Where it's white, I'll get a lot of reflection of light. So, if I run my laser beam down here, I get light, no light, light, no light, light, no light. And all those light on, light off, light, no light, light, no light, they form a code. And if I feed that into a suitable electronic circuit, I can turn that code into a picture, or I can turn it into music, or I can turn it into any sort of information I like. It's digital information, and this can be turned into all sorts of different things. So what I have on the CD is a line like this, with places on the line where it reflects light and where it doesn't reflect light. But the amazing thing about the line on this CD, the line on this CD is very, very long. If I were to stretch out the line that's engraved on this CD, it would go from Tashi Chodzong all the way along the expressway as far as Babessa. The line, with all the little marks on it that's on this CD, is several kilometers long. So how do I get it all on the CD? Well, imagine taking a long piece of string. Here it is. It's not quite 3 kilometers, but almost. How can I get this long piece of string into a small piece of plastic? Answer is by winding the string, up like this. And I can do many, 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 many winds, and I have got, in a very small area, and a very small volume, a long piece of, I've got my fingers stuck now, a long piece of string. Now, we do exactly the same with this 3 kilometer long line that's on the CD. Instead of stretching it out in a long line, we simply wind it into a spiral. I wonder if you can see, I've tried to mark a spiral on this DVD here. And I can get a very long line, which stretches from Tashi Chodzong to Babessa. I can get it onto one small compact disc. Now, so we've got a spiral line on there, but the amazing thing is, look at this here. The thickness of this line that's marked on the disc, the thickness of this line is 1/30th the thickness of a human hair. I could fit 30 of these lines in one thickness of human hair. So this line is very, very, very thin. And the laser light that shines on it is itself far, far smaller than the point of a pin. And this disc, when it rotates, means that the line is running under the laser light, and the laser light is flashing And this disk is rotating at 1,000 times a minute. So all this is happening with incredible speed. And it can only work because electricity does things so quickly. And if I've got a CD rewritable disk, it's even more amazing because there's a chemical on top of there, and as the laser hits the chemical, it burns the chemical. Sometimes it makes the chemical reflective, sometimes not reflective. And depending on the temperature that the laser makes the chemical, it'll reflect light or not reflect light, and the chemical can be changed. And this happens about 20,000 times a second on a line, a 30th of the thickness of the human hair, on a disk which is rotating 1,000 times a minute. It really is magic how a DVD player works, how a DVD disc works, and none of it could happen without the discovery of the laser. Now, one of the things that you've learned about in school is a phenomenon of light called total internal reflection. This happens when the light rays go from an optically dense medium to an optically rare medium, across a boundary, for example, going from glass into air or from water into air. Now, total internal reflection is very useful, and we depend on total internal reflection for our mobile phones and for our international communications from Bhutan. In the past, if we were going to talk to London from Bhutan, we would have a radio signal which went from a satellite dish up into the sky to a satellite and then back down into London, a total journey of about 150,000 kilometers. Now, we do not use radio signals to communicate with London. We use light waves. And the light waves are fed down a light pipe. That is to say, a pipe which controls and feeds and guides the light waves. And how does the light pipe work? Well, it works with total internal reflection. So here we've got a fiber, a very thin fiber made of glass there. And somewhere or another, you probably can't see it, but I've got it in my hand there, is a fiber made of glass. It's less than the thickness of a human hair. We feed the laser light into the end of this glass fiber, and it bounces off the sides like that and continues a long, long way. The fiber holds in the light waves just like a water pipe holds in the water. How does it do it? Well, if we look at where it bounces off here, it bounces off because of total internal reflection happening here. So total internal reflection causes the light to stay inside this glass fiber, and it can travel hundreds and hundreds of miles. In fact, this is the way in which telecommunications now go from Bhutan to Hong Kong and to London. In the past, it was radio waves. Now, it's light waves. So the laser and the simple phenomenon you learn about at school of total internal reflection are all responsible for our ability to receive the internet and to make telephone conversations all around the world. The fiber optic cable. And this is what is used in Bhutan Telecom now to get our signals, our voice communications and television communications across the world. Let's go and visit Bhutan Telecom. So we've come to Bhutan Telecom again to meet Nedup Dorji, the CEO, and I hope Nedup will be able to show us the sort of fibre optics that are used in Bhutan Telecom. Nedup.
Okay, thank you, Michael. What you see in my hand is a strand of a fibre optic cable. It is as thin as a human hair. We use fibre optics a lot in Bhutan Telecom. Okay, fibre optics are made of glass. I mentioned that fibre optics are made of glass a little earlier. To protect the fibre optics, they are shielded in plastic cover. Okay, so this is an example of one. This one is an armored, shielded fibre optic cable. We've got 48 in the core here, and this is what is used to connect one place to another.
Thank you very much, Nedup. So this has replaced the old satellite dish and the radio waves. We now send light down these 48 fibre optic strands, and it will go all the way to London and Hong Kong. Instead of radio waves, we're back again to communication with light waves.